Let us start with the second video with the medium transmission lines. In the previous session, we talked about short transmission line. Now we'll go for medium transmission line performance analysis. So here, when it comes to medium transmission line, the effect of capacitance in the generalized model cannot be neglected. So there are two configurations. One is T model, the other one is pi model. So let us see one by one. First, we'll be starting with nominal pi model. Nominal pi model in the sense, in the transmission line, it contains line impedance and then capacitance. Capacitance is divided into two equal halves and represented on either sides of the series impedance. This is the series impedance of the line, and capacitance is divided into two equal halves and represented on either sides. So this looks like the shape of a pi and hence called as nominal pi model. Now, before going into the analysis part, I would like to first tell you, you very well know that Ohm's law is given by V is equal to I into Z. So current I is given by V divided by Z, which is 1 by Z into V. You know that 1 by Z, 1 over impedance is nothing but admittance. Reciprocal of impedance is admittance. So I now is equal to Y into V. So instead of writing V by Z, we write Y into V. Please remember this so that it becomes easier during the analysis. Now, if we have to first find the ABCD constants, you know the approach that we have followed in short transmission line. We use KVL and KCL. So let me use KVL in this particular loop. So if you use KVL in this loop, voltage across this capacitor should be equal to voltage drop across this particular line plus voltage across this capacitor. So voltage across this is nothing but Vs. So I'm writing Vs here is equal to voltage across this capacitor, which is nothing but Vr, plus voltage across this particular section, which is I into Z. Let some current I flow and the impedance be Z. So Vs is equal to Vr plus I into Z. So Vr is taken as it is. Now in place of I am using KCL and I'm writing this expression. Let us see how we are writing the expression. Now this current I is set to flow in this particular section. Now if you apply KCL at this point, current I is given by sum of this current plus sum of the current flowing into the capacitor. I am repeating, current that is flowing in this section is equal to current flowing here plus current flowing through the capacitor. So that is what we are writing. It is given by IR plus IC1. So it is IR plus, instead of writing IC1, I try to write the current in terms of product of admittance and voltage as we had done here. So the applicable voltage across the capacitor is VR and the admittance is Y by 2. So this current is given by VR into Y by 2. So it is IR plus VR into Y by 2 is the expression for current I, this multiplied by Z. Now we just multiply this and split the brackets, IRZ plus VRZ into Y by 2. Now here I am again grouping this in terms of VR and IR. So if I take VR common factor, I have 1 plus YZ by 2 within brackets plus Z into IR. This is equation number 1. Next we'll be applying KCL. We'll be applying KCL at this particular node. So if you apply KCL here, current that is entering this node is equal to current flowing into this section plus current flowing through the capacitor. I repeat once again, current IS is entering here at this node. Part of the current flows through the line, remaining flows through the capacitor. So same thing I'm writing here, IS is equal to I plus Vs into Y by 2. The current that is flowing here is capital I, and the current that is flowing here is written in terms of product of admittance and voltage, as you have seen here. Current is voltage into admittance. So admittance here is Y by 2, voltage is Vs. So it will be Vs into Y by 2. Next what we'll be doing here is, this current I, already I have written the expression for I over here. This I is nothing but IR plus VR Y by 2. Already we have derived that I am using it here. In place of I am writing IR plus VR Y by 2 plus, next you are having Vs and y by 2. Vs already we have derived here in expression 1. This I am substituting here into y by 2. So just try to understand. In place of I, whatever I've got here, I am putting it here. Then in place of Vs, I am substituting equation number 1, whatever is there here, I am substituting, simplifying this step by step. After simplification, you'll be getting the expression Is is equal to y into 1 plus yz by 4 into Vr plus 1 plus yz by 2 into Ir. You just have to work it out manually so that you can understand. Now we try to compare it with the standard expressions and get A, B, C, D. So A and D are equal to 1 plus yz by 2, B is z, and C is equal to y into 1 plus yz by 4. So in case of short transmission line also, we try to get the expressions for Vs and Is. Here also we are doing the same. I've got the expression for Vs, I've got the expression for Is. So Vs, Is on left side, and in terms of Vr, Ir on the right side, if you write it in matrix form, compare it with the standard model, similar to short transmission line, you'll be getting the ABCD constants. Now we'll go to the phasor diagram part of it. So before that, these are the performance equations. From the circuit, we know Vs is equal to Vr plus I into Z. Current flowing through the capacitor IC1 is voltage into admittance, corresponding admittance, and IC2 is Vs y by 2, and current flowing through the line is IC1 plus IR, Is is equal to IC2 plus IL. All these things already we have used. Along with this, regulation is nothing but given by Vs minus Vr by Vr into 100. Efficiency is output power by output power plus losses into 100. This is very much similar to short transmission line. So this finishes with the performance equations. So far we have dealt with the nominal pi model. We have understood how we got the nominal pi model, and then in order to get the ABCD constants, we have used KVL and we have used KCL, simplified them, and after simplification we have got the ABCD constants over here, and then we have written the performance equations. Last part is the phasor diagram. Now let us try to understand the phasor diagram step by step. So now here we have the same circuit. This current through the capacitor, I have called it as IC1, and this I have called it as IC2. And you know the current that is flowing through the line here is IL. This is the receiving end current, this is sending end current, sending end voltage, and then receiving end voltage. So now let us draw the phasor diagram step by step. Initially, I'll take this receiving end voltage as reference. So that is the first step. I take Vr as reference. And since the load here happens to be lagging in nature, current lags the voltage by some angle phi r. Ideally, if it is an inductive load, current should lag the voltage by 90 degrees. But since we are not taking ideal condition, we take that IR is lagging phi r by an angle phi r. IR is lagging VR by an angle phi r. Next, so we have represented VR, we have finished representing IR. Next, we'll have to talk about current flowing through the capacitor. See, this is the voltage VR and this is the current flowing through the capacitor. Voltage across this capacitor is VR, current flowing through the capacitor is IC1. So always current through a capacitor leads the voltage by 90 degrees ideally. So here I'll be representing IC1 set to lead this VR by an angle 90 degrees. So this is the next step. So I have represented VR, IR in the previous step. In the second step, I have represented IC1 which is leading VR by 90 degrees. Next, see, now we have finished with VR, IR and IC1. If you apply KCL at this particular point, sum of IR and IC1 should give me this current IL. So I just have to add IC1 and IR. So that's what I am doing in step number 3. I am adding this IC1 with IR and I am getting the resultant IL. So this is the resultant IL. This is what happens in step number 3. Next, coming to step number 4, that is over here. Now I have finished representing VR, IR, IC1, IL. Next I should look about look for voltage across this particular line. Voltage across this line is nothing but voltage across the resistor plus voltage across the inductor here. So current and voltage will be in phase for a resistor. So what I'll do is, at this particular end, I try to draw a line parallel to IL, which represents IL itself. Now since current and voltage are in phase, product of IL into R represents the voltage across this particular resistor. So IL is in phase with IL into R. Voltage across the resistor and current through the resistor are in phase. Now coming to this inductor, you know, for an inductor, current lags the voltage by 90 degrees. Our voltage is set to lead the current by 90 degrees. This is the current, which is IL. So this particular voltage is set to lead this particular current by 90 degrees. So I have IL into X, that is being represented here. See, this is actually cancelled, don't worry about it. This is ILR and this is IL into X. Next step, if you apply KVL in this particular loop, voltage across this capacitor plus voltage across this particular line will give me voltage across this capacitor. Voltage across this capacitor is VR. Voltage across the line is already found, that if you add these two voltages, you should be getting the voltage across this capacitor, which is Vs. So in this figure you can see ILR plus ILX will give me voltage across the line, and here already I have VR. If you take the resultant of these two, we'll be getting Vs. So now we have got supply voltage Vs. In the phasor diagram we have represented Vs. Now we are left out with Is and IC2 has to be represented. Once you have represented Vs, IC1 can be represented because current always leads the voltage by 90 degrees ideally in case of a capacitor. So in the last figure here you can see I have represented IC2 leading this particular Vs. This is Vs. IC2 is leading Vs by 90 degrees. So I finished with IC2. Last case is I have IC2 now, I know IL. As per KCL at this point, if I add IL and IC2, I should be getting back IS. So that is what is done in the last step. IC2 is added with IL and I'm getting the resultant IS here. See here carefully, this is IC2 and already we have IL here. If we add these two, we'll be getting back IS. So this finishes with the phasor diagram for nominal pi model of medium transmission line. In the next video, I'll go for nominal T arrangement of medium transmission line.